Welcome back. I hope this is working. I actually didn't test it. Let's see. Mic. Yeah. Oops, sorry about that. That was just me testing the mic. Seems to work. Welcome back. So we're doing extremely open science today, continuing our project of looking at how mutations, including small indels, affect genome quality. So let's do a recap of where we were. So let's just go back. Oops. Oh, exactly sure what I did here. Oh, yeah, okay. I was playing around with this a bit. I'm just going to clean that up. All right. So this is what we've been playing with. Let me just remove. I'm going to keep that for now. So this is what we've been playing with. So last week we actually first solved this mystery of what had been going wrong with the stream, or what had been going wrong in the previous stream, because we had seen these artifacts, and it turns out that CheckM2 we were running it through a couple of layers because we run Jug. Let me just maybe adjust the camera a bit. I'm going to zoom out myself a little bit. How do I do this? Yeah, so that because I sometimes I always have to remember to clean the whiteboard behind me to make sure that there's nothing, there's no information that I wouldn't be 100% comfortable sharing on stream. But back to where we were. So 2 weeks ago we had seen a very strange result, and last week we showed you that this was happening because CheckM2, we run it, we have Jug that then calls conda environment that then calls CheckM2 that then itself runs these other tools, and if we press Control C at the wrong moment, or it's a little bit hard to trigger, but you can trigger this where CheckM2 keeps running in the background even though you've interrupted the other programs, and so you can end up in a situation where you are running two instances of CheckM2 that are writing to the same outputs, and then they start fighting, and this is a problem, right? So what are we going to? So we solved that, and then once we solved that, we saw that that things were back, quote unquote, back to normal, and in particular, where's the E. coli? E. coli, yes, E. coli, CheckM2. Check2, E. coli. Yeah, so the E. coli looked like this, which is what it looked like before, where, so here's completeness by CheckM2 sort of goes down, and maybe there was here, no, not this direction is the one. So you can, right, this is, at the beginning, you can see that there's a bit of a plateau, and then it starts to go down. I also commented that, we've been looking at 50,000 mutations. This is a really large number, probably, and we're going to do that. This stream. Let's narrow it down. I think 5,000, which is what we've been looking at, is probably. So we've computed 50,000, and then often we then narrow it down to the 5,000. This is a more reasonable number of mutations. I mean, it's still a very extreme. I think maybe this area here is what is more realistic. Anyway, so so that's one change we're gonna do. I'm going to purposely do that towards the end of the stream, for the very simple reason that if we do that, that's going to change a lot of them. That's going to require recomputing all the CheckM2 stuff, and so I will do that change. I will then just run it off stream. So we saw this, we fixed this, and then we started to look into the CheckM2 outputs, because we saw that so the way it works, it looks into KOs. So KOs is K-orthologous group, and as the number of mutations increases, and here again, let's just look at the up to 5,000. So if we take the 0 mutations as the ground truth, so we can see that as so on the here green is false negative, so this is KOs that are missing, and you can see that the scale is on here on the left, and this orange is the false positives. So they both increase, but do note that the scales are different. So you have a bit more false positives, KOs, but many more missing KOs. And so today I want to go again, look into this, or now dig into this a lot more carefully. So let's move this. So what's happening here? So let's try. I'm gonna pick E. coli just because E. coli is nice. So let's go back and outputs. So there's a okay. So I'm gonna pick E. coli. I'm not even exactly sure what I'm looking for, but maybe what I'm looking for is a gene. Let's look at genes that disappear with the mutations, these so-called false positives, and see what happens. Or actually, let's just play around with this a little bit. I have a bunch of related questions, including, for example, even the genes that don't disappear, do they become shorter? So the same. So let's just play around with this a bit. So I'm going to start a file. I'm going to call it explore. I'm going to use okay, and let's okay, okay. Sorry, this is a yes. Okay, this is just okay. So this is what we saw last. I'm trying to run check M2. Oh no, it was in the plot. Check M2, and then yeah. So we would load the check M2 outputs, and then we're not doing pandas, we're doing polars. Sorry, force of habit. Just get rid of pandas. All right. Let's just do this same. Okay, I'm gonna do this. Gonna copy over. Okay, so this is the code we had. We just get all of diamond outputs. Remember, the diamond outputs basically mean they're just, the different files are just all the same. They've been split off only for because if the one file is too large, they get split off, and now we end up with this data. And maybe what I want to do here is actually let me just is actually let's maybe compare just the number of maybe two. Let's get let's do this. Let's compare just one. No, not this one. So this would be with one, and again, so this is why this is a little bit. This is why I was taking such a large number of mutations before, because we're looking for these extreme extreme cases, somehow a little bit like looking for extreme phenotypes, even if the extreme phenotype is not really representative. And so let's look at this too. So 0 mutations, and let's call it wild type, and okay. All right, so we have, right, so, okay, so we have, yeah. We have about 3,000, and, you know, just about 3,000 KOs, of which 145 get lost, and 50. Okay, let's look at the ones that get lost. Okay, I'm actually not sure what I'm going for here. It's a bit too much. So what I want to, what am I looking for here? I'm gonna get my thing here. Do a little bit. Let me do a little bit of. A second. Second. 2 seconds. I'm just connecting something here. Sorry, and okay, I just need to connect something here for 1 second. Yep. So all right. So this is the. Yeah. So this is. Right. This is basically this. Right. So here I can do. So I can draw hello. Right. All right. So what I'm now going to be looking for is, so I have the 0 mutation. Let me redraw that. The 0 mutation. And the 1000 mutation, and this has a bunch of genes, but what am I looking for here? But maybe it would be interesting also to see this correspondence. So for example, most genes will probably correspond 1-to-1, and then some will get broken up or disappear. So this would mean looking at the prodigal outputs. Okay, let's do that. Yeah, all right, so yeah. Let's do that. Let's look. So we have the protein files. So I said, let's look at 000 FAA. Okay. Right. So we can parse this very quickly and get the. Yeah. Let's do that. Let's parse this and get the genes, and then parse the other one, get the genes, and that will give us, yeah, that will give us what? Well, that will give us something. Get gene positions. So, actually, yeah, that's bad, but let's do some. Sorry. Alright, famous last words. Let's use regular expressions. Let's do a quick regular expression for this. So it would be prodigal fast. So something like this. Oops, sorry. Sorry, what did? So I think this works. Okay, if it's this, yes, but yeah, this is the correct order. Okay, yeah, this. Oops, so config start, no, config, so this would be config gene ID start and is reverse. I think this is it. Start yeah, that's pretty correct. Yeah, this is pretty good. Okay, that's not bad. Okay, yeah, no, okay, now I guess this is the part where we have to look into the polars data frame. Okay, yeah, just data frame, okay, data. Is this even a thing? Okay, it seems to work. Okay. Okay, why not? Actually, okay. What about this? Yeah, this seems to work. Okay. Okay. Oh, okay. All right. So let's see how this works. So if we, our intuition should be that now if we compare the start positions, we should have a lot of common starts. So there should be more common starts than common ends. Okay, so let's okay, that's actually really surprising. Oh, of course, right? Because the the positions shifted. Yeah, we have an indel, the positions all shift. Okay, yeah, it's annoying. Yeah, it's pretty annoying. Okay. Okay, this is annoying. So we're gonna have to look at the actual sequences, right? If we look at the actual sequences, that would not be. So we're still looking for instances where the original. Let me just check whether the original is not. Okay, so we could load all of them, all of the actual sequences, and look. Okay, I'm gonna copy this file from the semi-bin. So this is a very simple file, or a very simple function, FASTA iter, iterates over all sequences in a FASTA file. It's very, very simple. It's just very lightweight. I don't want to be importing BioPython because that takes, that will lead to 50,000 dependencies, and so I just want to import from FASTA. sorry, it's the only. Yep, this is. Okay, so let's just check. Yeah, so this is. Let's just check something like, for example, like this. Starts. Let's just check the first, I don't know, let's say 30 amino acids. Okay. Okay, let's actually check. Okay, so if we check all of the sequences. Okay. Okay, so this is something, right? So if we look at the exact sequences, we lose about 400 of them, or there's some mutations in 400 of them. But normally the beginning is let me look at this a bit. Okay. Okay, let's do this. I think this is not going to take that long. Yeah, let's get rid of the again, immediately starts to go down. It's interesting. It goes down. Could always. All right. then okay. No, okay, I know something we could look at. I mean, we could look at this, right? So if we have, again, we have, so let's say we have this 0, which wild type, and we have the 1K mutations. And here we have the KOs, okay, 1, 2, 3. Let's look for, where we do have the same K 1, 2, 3. We know that this is going to be gene, let's say 5, 5, 6, 7, and this is going to be gene 8, 9, 10. What are the sizes of these? Yeah, this could be something. All right, let's do that. Let's do it that way. Let's look at that. Have this, okay. Common. Let's remove that stuff. Oh, let's keep that stuff for now. Common, alright, so okay, so we have, for example, this one, K. So we can look at what are we looking at? Yep. Filter. Did I call it moot 1000? Okay. All right, let's do the other one. I mean, or let's do this. So if we do it this way, okay. Yeah, this is basically, okay, this would work. Something, okay, this would work. Okay, I'm gonna okay. All right, so this. Yeah, okay, yeah, we can see that, yeah, the IDs change because everything changes, right? But, get, okay, I'm gonna change this a bit. Change this a bit. Okay, so that instead of getting the config, separating the config and the gene ID, let's just get both as. Right, so that exactly. And this should be exactly, this is what we were looking for. Okay. Let's just call it data. Okay. Perfect. Okay, so we have the same KO, but it's shorter. This is nice. Okay, and this is something we can. Right, now I want to do, and often I do draw these things out. So now I want to do one of these plots that looks like this. That looks like this. So I want to have wild type. Okay. Here. Let's do that. So here. So this is size. This will be a dot. This will be a dot. A line connecting them. And then some sort of box plot. Right, this would be the plot. So let's do that plot. Okay, and I guess this is. So where's the? Okay, there it is. We have C1. Yes. So this is not the right for a for yeah, this is bullshit, right? This is not what we want. Yeah, this is looks something weird. Yep. How do we iterate over? Iterate. Data frame iterate. Iter rows. Okay. Will work. Check what this is. So the row is row. Yeah. Okay, I don't like the name because I thought it was going to be a named tuple, but no, it's going to be some weird little thing. So let's just do this for okay. Yeah, all right. It's a little bit hard to read, I guess. Plot the ones. I don't know what's red. And now we want to have something. Yeah, this would. Does this even exist? No. Yeah, we want to do something like the melting thing. So polars melt. Does this exist? Melt. Yeah, this is what I want. Moxpod data x equals work. Yeah, this is pretty. Okay, so here what I want to do. Okay, so first of all, let's put the okay, yeah, so most of okay, where's line width. So I want them to I find them too wide. Oh, find. Yeah, that's what I want. Pretty, okay, this is probably closer to what I want. Yeah, that's nice. Okay. Right. This is nice. Line width. This the line is a bit too. Yeah, a little bit nicer. Let's actually do it the other way. Yeah, let's do it this way. Yeah. It's correct? Yes. Okay, so there are some instances where, yeah, so here we can see 3 cases. So there are some, so right now, so the black just means let's let's remove some noise. Okay, but now we have 3 cases. So if the one is smaller, then we print it out in red. If it's less than 10, then we actually just don't do anything. We don't even put it out. And then otherwise, we yeah. Okay, I like this. Okay. The only thing is the 1K. It's a bit too much. Let's do this intermediate one, which is 100. Okay, and now oh, we don't have 100? Oh, okay, I see. Okay. This is pretty bad code. We will not commit this to the main repository. Okay, this is alright. Okay. Okay. Okay, I think this is wrong. Just check if that. Okay. Okay, this is right. Okay, this is wrong. Yeah, this is wrong. Okay. Yeah. Okay, let's do a clean. Where's the okay? Okay. Okay, yes. Right, good, nice, okay. Oh, yeah. All right, okay, this is it. Okay, this is the end of today's session. Okay. Get this and boom. All right. Okay, this is what we want, this is what we get. And now I'm just gonna save this. I'm gonna rename. All right, now let's all right, I'm just gonna quickly go over this. Actually gonna do this. And in the meanwhile, notes. So today is 18th. Yeah. So explored length of Earths by KO in equalized simulations. And the other thing, as I said, changed mutations, changed the number of mutations in simulations. Max 5k by steps. Okay, and this is one thing I still want to do. Okay, so I'm actually going to do that first. Mutations, so here, and so just to show before. So this is before I save it. So before I save it, everything has been run. There it is. Very nice. Now, after I save it, unfortunately, so we need to rerun the checkm2 because it runs the whole batch at once, and then we need to run a lot of these. So I will do that off stream and then just show the results quickly in the recap. So I'm gonna add this, and I am going to simulate. I mean, yeah. Oops, sorry, I did not actually. Okay. And then, yeah. I'm going to. What did I call the other branch? I'm gonna I'm gonna call it a work in progress batch. So as I said before, but this was not a big deal. This is not always a big deal, but so normally I would not be committing this code. I think this code is still really just exploratory, preliminary, and so I would not be committing it. And I would be working on it for a bit longer and then eventually probably commit it. But for the sake of this project, what I'm going to do is I'm going to create a separate branch. I'm going to call it work in progress, and I'm going to commit that so that if anyone out there wants to check it out, everything's public. This has always been extremely open science, right? That's in the name. Stream notes, and okay, and so this plot that we just saw, so this was, this is this is basically what I would wanted to see, because right, so we saw before the overall gene length. So this is the box plots, and obviously the box plots, they do show a difference, maybe not here, but here you see that there is a slight decrease, but this is masking. In the box plots you have KOs that are very long and then drop. And so I think if we can do this by KO, we can try to recover this very large drop in, I know this is, if the average KO is supposed to be 1,000 amino acids, and in this case it's only 500. That's a huge drop, even though overall the genes in a genome, the drop might have been much smaller. Actually, maybe it would have been interesting to plot this. Okay, I'm gonna. All right. I'm gonna just really very quickly do the plot, but do it. Color it by the. Just do the colors by the difference in the 100 and not the difference in the 1,000. There it is. Check that length by KO. Yeah, this should have been it. All right. Sorry, is this correct? Yeah, there it is. All right, so if we do it by the difference in the 100, there's only a few, but you can see that there's, look, even 100 mutations, there's a huge drop there. So I guess the next step would be, could we potentially even recover, identify these cases? And even though there's not most of them look horizontal, if we could identify these cases, would it be possible? And here it's very clear because we know that what it's supposed to be. Right, so we'll be looking into that. Okay, so no, I'm not saving that one. What I am doing is, what did I do? Yep. Okay, I'm not going to save that one. So what I am doing is I'm going to be pushing this work in progress. Yep, I'm gonna push this. I'm gonna push the main branch. Right, so I am now actually I am going to now I'm going to start. Yep, as I said, I'm going to start this. It's a different project. I'm going to start the simulation, let it run. I'll put out the results in the recap video. I'll post to the mailing list, and I will see you all next week. So have a good week and talk to you soon.